All right, here's the last section. We got dilations and similarity transformations. All right, so you got a couple of these here, a couple of vocab words: non-rigid transformation, a transformation that does not preserve distance and angle measures. All right, and the ones I will be talking about today are dilations. So you have dilation, the shrinking or growing of a figure proportionally by a common scale factor. So most of the times we will do scale factor. Scale factor, remember, usually we want to say new over old for this stuff. And we did that in our previous unit, so we'll go image over pre-image to figure out what the scale factor is. All right. A reduction, that's a shrinking of a figure with the scale factor being between 0 and 1. So that means the image or the new is smaller than the old. And then an enlargement is exactly what it sounds like. It's when your scale factor is bigger than 1, so that means that your new figure becomes a little bit bigger. Coordinate notation for a dilation. This means here, so you're going to put a D, and then you're going to put what number, your scale factor, whatever that is. And then you do that to each X, and then comma Y for that. All right, so then that means dilate X and Y by multiplying each by 2 right there. X comma Y by multiplying by 2. All right, and that's assuming that your point or your center of dilation is 2. Is the origin, and most of the times in the class that we're teaching here, we're going to assume that we're dilating with respect to the origin. If your center of dilation is somewhere else, it's actually kind of complicated. It's probably kind of a pre-AP concept, essentially. But what you essentially have to do is you have to do a translation first, then you go dilation, and then you translate your figure back. So it's a lot of steps. We probably won't get into that today, but there are some good examples on the internet if you search for it. So anyways, so we're going to draw quadrilaterals A, B, C, D with those vertices there. So 2 comma 0. There's A. B is 6 comma 4. 1, 2, 3. Oh, negative 4, I'm sorry. C is 8 comma 2. And then D is 6 comma positive 4. So actually it wound up being a point up there anyways. There you go. So I'm going to connect those. All right, so then what we're going to do is, dilate this figure, and we are going to do it with the scale factor of 1/2. So essentially all I need to do is take those points and multiply them, and I got them here on my notes, so I'm going to zoom in here and just kind of write them down. So A was 2 comma 0. So if we do 2 comma 0 times 1/2, that'd be 1 comma 0. All right, and you do the same for each point there. So I think B was 6 comma negative 4, so that'd be 3 comma negative 2. C, that was 8 comma 2, so divide those both by 2. That would be 4, and then comma 1. And then D was 6 comma 4, so that would be 3 comma positive 2. Those would be your new points there: A prime, B prime, C prime, D prime. So I'll go ahead and start plotting those. A prime, B prime, 3 comma negative 2. C prime is 4 comma 1. And then D was 3 comma 2. So it should look like the same figure, except scaled down. All right, and since the center of dilation, since that is, here we go, just lining that up. Since the center of dilation was the origin, each of these points should be like half their distance from the origin here. So I'm going to line these up just to kind of show you that. So like A right there, that's the easiest point to see. It's half the distance A prime is half the distance that A was. Now if you go look at, like for example, D, notice they lie on that same line right there, except D prime is half that distance right there. And then you can do the same thing for B right there. B should be half that distance, B prime and B. And the same thing for C. So all those distances are half as much. So let's see if I can plot that back there. Okay, there we go. So anyways, I just wanted to line those up there to kind of show you what that looks like. So I guess this next one here, a triangle has these vertices here. Find the coordinates of LMN, so that LMN is a dilation of BCD with a scale factor of 4, and then sketch both of those there. So -1, -1, that's for B. Nope, I don't want to paste. There we go. So there's B, C is 0, 1. And then you have 1, 0 there for D. So I guess we're going to take that. We're going to do a scale factor of 4. Essentially, that just means multiply 4 times everything. So L, I guess, was going to correspond with B. So L is going to be -4, -4. Okay. I guess C, or not C, I guess we need to use the correct letters. M is taking the point C and multiplying that by 4, so that'd be 0, 4. And then that last one, N, was taking D and multiplying by 4, so 4, 0. Let's do those, I guess, in blue. -4, -4, 0, 4, 4, 0. Should be dilation there, with the center of dilation being the middle, the origin. So yep, there's your points. Go back and label them. You had L, M, N. There's a dilation, so the scale factor of 4. So yeah, these are relatively easy. They're not too hard here on these. We can get back into similar triangles. We did that, last unit, I guess. So, or a couple units ago, depending on when you were watching these. But yeah, you got some scale factor going on here. Remember, you want to go new over old here. So they say DE. Okay, ABC is the original, and then DEF is the new, or the image. So DE probably goes with DEF. So you're going to say 6, and then over 4 right there. So that's a 3:2 scale factor. Or you could say 1.5. Okay, so that stuff's pretty easy there as far as finding the scale factor. We've been doing that for a while, just thinking in terms of transformations. ABC and DEF are similar. AB is 2, and it is dilated by a scale factor of 3. What is the length of DE? So this is like starting with the side length and then starting with the scale factor. And then if you multiply those, DE should be 6. And then there you go. That's really all you do there for that. So scale factor, pretty simple there. You also have other non-rigid transformations. You have compressions and then stretches. And we just get into this just a little bit, but you'll do it quite a bit, probably in Algebra 2 and then especially in Pre-Cal if you go on to those classes. So this is only like changing, like maybe the x's or just the y's when you're doing a compression or a stretch. So compression, a transformation that decreases the distance between points, and a stretch, a transformation that increases the distance between points. You can change the size of a figure in the coordinate plane by multiplying the x and y coordinates by different factors. Alright, so this is a little bit different than dilations. So for example, you can do what we call a horizontal stretch. So imagine I wanted to take these ends right here and then pull them out and stretch it horizontally. It'd make this wider looking triangle right here. So that's if you're doing a horizontal stretch right there. And remember, stretch, we think of getting bigger. So A, or whatever you're multiplying by, would be greater than 1. So you can also do a horizontal compression, which means like the number that you're multiplying by, maybe it's like half or something like that. So that's where you push in the sides, and it makes it look a little bit flat or a little bit narrower, I guess, and not as wide. So then here's what that triangle would look like right here. That's kind of highlighted there in blue. So that would be a horizontal compression. You can also do vertical stretches. So that's basically taking the vertical points right there and then pulling those out, up and down. So then there's your new triangle right there. That's a stretch. That means the number you're multiplying by is bigger than 1. And notice here too, I kind of forgot to hit on this. Notice that you're multiplying the y value since it's a vertical stretch. And then if you're doing a horizontal stretch, you take your x values and you go and multiply them. Okay, vertical compression, that's basically just saying if you're like multiplying by a number less than 1, so like maybe 1/2, that's taking all your ends and then smashing it down vertically. So it's, it's compression. So it looks like this right here. So just taking it and kind of flattening it like a pancake or something like that. So it's pretty straightforward. The notation is not really that hard. This says take each x, y. And this is a little bit different than your coordinate notation that we've done a lot. But this is saying take each x comma y, and then we're going to multiply the x's by 2, and then, or I'm sorry, the x's by 3, and then the y's by 2. So I'm going to go ahead and write out the image, or e prime, f prime, g prime, h prime right here. So we're going to take those and you're going to multiply the e, you're going to multiply that by 3, so that'd be -6, and then take your y, you're going to multiply that by 2, so that's a 4. So actually this one here is just going to be a horizontal stretch and a vertical stretch at the same time, but you're not doing it by the same number, so it's not considered a dilation. So multiply 3 times x, 2 times y, we got -6 and then 4. So then let's do f. So that'd be 3 times 2 right there, so that'd be 6. And then you got 2 times 2, so that'd be 4. Okay, looks like g prime, or yeah, g prime, so 3 times 2 right there, so that would be 6 again. And then we got 2 times -2, so that'd be -4. And then let's do this last one here. Yes, let's just keep the same color. -2, so 3 times -2, that'd be -6. Oops. And then the -2 right there, if you multiply that, that would be, I guess, a -4. Oh, that's h prime. And then graph the image. And I'm going to go ahead and graph the original as well. I'm going to graph the pre-image just so we have it. So -2, +2, 2, 2. Oh, so this is looking like it might be a square. 2, -2. Yeah, so this thing's taking a square. And then we're going to do a horizontal stretch and vertical stretch at the same time. So there's your points. If I go plot my new ones, you got -6, +4. So there's e prime. You have +6, +4. There is f prime, g prime, and then h prime. So it makes it into a rectangle. And I like this example here because we're scaling the x's and the y's by different numbers. So it goes from a square, it kind of looked like a square originally, and then it goes to this more of a rectangular shape. Okay, so how's the transformation? What if we did 2 times the x's and 3 times the y's? What if we did 3 times the x's and then 2 times the y's? Let's see how that differs right there. So I think originally up here we did the 3 times the x and 2 times the y. So let's see how it's different. This right here, it's right here it's only 2 times x, and then 3 times the y values. So essentially it's going to make it more taller than it is wide, essentially. That's what I would put there. Let me see if they had anything else written for that one on the notes. Yeah, that's about it right there. So we'll move along. Um, so is this thing a vertical compression or a vertical stretch if we're going from STW to S prime TW, STW prime, I guess, right there. And what's a coordinate rule here? So look at this here. Now notice the horizontal values. Those aren't changing right there. So this is strictly a vertical thing. So here's our original. And then it looks like it's getting smaller. Looks like we're pushing in the sides right there. So I'm going to say that this is a vertical compression right there. And then we got to figure out by how much. All right, so look at your order pair up here. This order pair by T, that is -3. And then here's that key point is the Y is 4. And then notice that T prime right there, that's -3. But then check out the X value, it's 1 right there. So we want to think about what we need to multiply 4 by to get 1. All right there. So you want to say it's kind of like multiplying by 1/4. Or you can almost think about it like scale factor. Just do the new y over the old y right there, or 1/4 right there. So it's you're compressing it by, I guess, 1/4 here. And the way you would want to write that is you're going to say we're going to take each x comma y, and the x's stay the same, but the y's will be 1/4 as much. So 1/4 y for that one. That'd be how you write that. Okay, let's see what's going on here with this one. ABC has these vertices, and then after a dilation with a scale factor 2 centered at the origin, followed by a horizontal stretch of 2x and then y. So I guess we're going to dilate and then we're going to stretch horizontally after that. So you got a couple of different things you're going to do. So let's do the scale factor of 2, the dilation, which means you take everything and you multiply it by 2. So I'm going to take each of these order pairs and multiply by 2. So that's going to get us -4, -4, 0, 2, and then 0, -2. Oops. So those are your new points there. I'm going to go ahead and plot some of these as well. So -2, -2, that's A. B is 0, 1, and then C, 0, -2. Oh yeah, so it looks kind of like a right triangle here. And then let's do these new points here, A prime, B prime, C prime. We'll do that in red. Oh, whoops, I didn't go far enough there. So there's A prime, and then B prime, and then C prime. We'll go back and get my blue lines. So there's those, and then after that we want to do the horizontal stretch by 2. So that means take each of these x values here and we're going to multiply them by 2. I guess I'll do that here in a different color. So those new points here, A double prime, that's going to be -8, but then the y value stays the same because they're not doing anything to that. So that actually doesn't change. 0, 2, yeah, that just stays as 0, 2. That's kind of strange there. And then this last one, I guess it stays as 0, 4, -4. So we'll see. We'll sketch that, see kind of what that looks like there. See what's going on. Let's do it. I guess here I'll do it in green. So 0, 2, that didn't actually change. So B double prime, C double prime doesn't change. But then that A double prime goes all the way out here. So -A4. So then it looks like you're stretching it out horizontally right there. That would be your answer there on that. All right, and that'll be it here for the lesson.